This fourth lecture on tensor algebra, we shall continue our discussion on vectors as a tensor of rank 1. We shall explore few further properties of vectors. Firstly, we want to express the group property or transitive property. Group or transitive property of coordinate transformation. What does it mean? Say we have a vector, either covariant vector or contravariant vector. If when expressed in S frame, we denote it as either covariant or contravariant like this. When we transform it into prime frame, we write it A bar alpha or, and we consider another transformation relation. Say we write it A double bar P. So if we consider this is the transformation, firstly we transform from S to S bar and from S bar to S double bar. The group property means that we can go from here to there in a single transformation. Let me first write the component A bar alpha. So, AI is equal to del xi del x bar alpha A bar alpha. And if we want to express this one, A bar alpha can be written as del x bar alpha del x double bar p A double bar p. This is the transformation relation from between S and S prime, S and S bar, and this is the transformation relation between S bar and S double bar. So if we use this over here, what we get? Del xi del x bar alpha, and for A alpha we write this part del x double bar p A double bar p. If we use the law of partial derivatives, this is simply del xi del x double bar p A double bar p. So this is the transformation relation from between S and S double bar. That is to say, we may go from some initial coordinate to final coordinate via several steps. But if we consider this composite transformation, then we have the group property. That is, two successive transformation is also an element of the group. This is called the group property or transitive property. And this same property can be proved for covariant vector, only the transformation relation will be different, and we can also prove it for tensors of other higher rank. But for the sake of simplicity, we proved this property or stated this property in connection with vectors. Another thing is that this transformation relation is being guided by the Jacobian, and this is another Jacobian. The Jacobian which connects between S and S prime is x bar, and that connects is x bar x double bar. So if we write this Jacobian x bar x double bar, then this can be written as the product Jacobian this is the property of the Jacobian. Another thing is that I want to address is when there will be no distinction between covariant and contravariant components. This, in fact, that if we transform from one Cartesian coordinate system to another Cartesian coordinate system, that is, we consider the transformation from one Cartesian to another Cartesian coordinate system, the transformation relation is linear. So Cartesian is to Cartesian S bar transformation. These transformation relations are linear transformation. Let me explain this first. Let us consider a coordinate system S. This is its coordinate axis. x1 axis, x1, x2, x3 axis. We transform it into another Cartesian system. The most general one that can happen is a translation by R. Then we land up with this coordinate system, intermediate coordinate system, and then finally we rotate this to achieve S prime frame. So the most general transformation that connects two Cartesian system is a translation followed by a rotation, or the vice versa. If we choose a point like this which has position vector r with respect to S prime, and we have the position vector r bar with respect to S prime, then obviously we know the Galilean type transformation relation is that plus r, which in component form leads as xi is equal to ai alpha x bar alpha plus xi, which obviously shows that del xi, del x bar alpha is equal to a of I. You recall that the rotation is being mediated or represented by an orthogonal matrix. So the inverse relation can be written as x bar alpha is equal to ai alpha xi minus x alpha. This says that, which shows that x bar alpha del xi is equal to ai alpha. So these two quantities are same, which is the main difference between covariant and contravariant vector. You recall that ai is equal to del a. This is the contravariant vector, and the covariant vector is del a bar alpha del x I a bar alpha. So the main difference is, apart from notation, the main difference is these derivatives. And for transformation involving two Cartesian coordinates, the general transformation involving two Cartesian coordinates has the property that this is equal to this, and in which case there is no distinction between covariant and contravariant vectors. These are known as the Cartesian tensors. One more thing, that these AR alpha that we have talked about is the components of an orthogonal matrix. For an orthogonal matrix, I have AI, K, A, K, J summed over K is equal to delta ij, as we used to write in matrix notation. But in tensor notation, this relation changes to aik akj is equal to delta ji in tensor notation. Now we shall consider what is meant by the covariant and contravariant components of a vector. Its vector A may either be represented in terms of its covariant components or in terms of its contravariant components. So the same vector can either be expressed in terms of covariant vector A can either be represented in terms of AIs, or it could be as well be represented by covariant components. So it is the set of contravariant components and it is the set of covariant components. What is the distinction between these two? We can write the vector A, when we write it in explicitly, this can be written as A1, E1, A2, E2, and in 3 dimensions there will be third component, but we restrict ourselves to a vector in 2 dimensions. So these are the contravariant components of vector A, and this same vector A can be written as A1, E1, A2, E2. What is the meaning of it? Recall that the example of contravariant covector is velocity, acceleration, etc. And this is the example of our covariant vector is gradient. So we consider in an oblique coordinate system and or non-orthogonal coordinate system. So this is we have a vector. We have a vector A, and when we express in terms of tangent vector, so we have a 2-dimensional space and we express them in terms of tangent vectors. These are the tangent vectors. So this is the first one. So this is E1 cap, and this is second tangent vector E2 cap. So the component of if we draw a line parallel to this much is this much is E1 A1, this part, this part is this and this part is this much. We consider a normal basis. That is, if we consider this is the coordinate line, this is the line along which a particular coordinate, say theta increases. Then at any point we can draw two vector. This is the tangent vector, or we could draw the normal vector. In case of orthogonal coordinate system, there is no distinction between the space spanned by tangent vector and normal vector. But in the case of non-orthogonal coordinate system, there is a difference between normal and tangent vector. Let us consider this is the normal vector. And this is P2 vector. So these are tangent vectors and these are normal vectors. So what we do, we draw a line parallel to this. And another line parallel to this line has to be extended. So this much is, this is A1, E1 cap, this much. This is A2, E2, sorry, A2, E2 cap. Similarly, this is A1, E1 cap. And this amount is A2, so A2, E2 cap. So the same vector A, when expressed in terms of tangent vector, we speak of contravariant components. And when the same vector is expressed in terms of normal basis vector, we speak of covariant and components. The clue is that when we consider the velocity, as for example velocity, this is being directed towards along the tangent to the trajectory, particle's trajectory. So it is a contravariant vector. On the other hand, when you evaluate gradient, it is directed normal to the surface. So it is a covariant vector. The tangent and normal basis may also be looked upon as the reciprocal basis set. Say we have three vectors A, B, C to span a space, then we can define another set called alpha, beta, gamma. They are called reciprocal such that A is equal to B cross C, A dot B cross C. Similarly, beta is equal to C cross A divided by same thing, and gamma is equal to A cross B. These are the reciprocal basis set, which is something like that. You see that alpha is perpendicular to B cross C and so on and so forth. So this is the physical aspect of covariant and contravariant components of a vector. The point that I want to emphasize is that the same vector A can either be written in terms of its covariant components or in terms of contravariant components. This much with the discussion of tensor in connection with vectors. Now we switch over to tensor of rank 2. So we are going to define rank 2 tensor. In an n-dimensional space, a rank 2 tensors. In an n-dimensional space, a vector has n components. So in an n-dimensional space, there are n square components. In Rn, there are n square components. This square comes from the rank 2 quantities such that there are three types of tensor. One is that Aij is equal to del xi, del x bar alpha, del xj, del x bar beta, a bar alpha beta. This is called a contravariant tensor of rank 2. If their transformation relation between two, there are n square quantities Aij, and there are also n square quantities a bar alpha beta. If they are related to one another by this transformation relation, this is the contravariant tensor. Then covariant tensor of rank 2 is defined as Aij is equal to del x bar alpha, del xi, del x bar beta, del xj, a bar alpha beta. Note that the covariant component is written as subscript and contravariant component is written as superscript. And there are yet another type of tensor called the mixed tensor of rank 2, which is defined as Aij is equal to del x. I is the contravariant component. Recall that we are using the notation in S prime I, J, K. In S prime frame, the dummy indices are alpha, beta, gamma. We are maintaining this notation all along. The inverse transformation relation, that is what will be the expression of A bar alpha beta in terms of AI. In order to get the inverse relation, let us consider this expression. The first expression, Aij is equal to del xi, del x bar alpha, del xj, del x bar beta, a bar alpha beta. This is the relation. We multiply both the sides, these sides, we multiply with del x bar alpha prime, del xi, and this is del x bar beta prime, del xj. And since the indices are repeated, the sum over I and j is implied. So we multiply this side is del x bar alpha prime, del xi, del x bar beta prime, del xj. Now, if we we rewrite this expression as del xi, del x bar alpha, this one, and coupling with this, del x bar alpha prime, del xi, sum over I is there. Then the second coupling is del xj, del x bar beta, and this term del x bar beta prime, del xj, and multiplied by a bar alpha beta. This part is a delta function. It is a delta function of alpha prime alpha, and this part is another delta function. This is beta prime beta, a bar alpha beta. On the right hand side there is a sum over alpha and beta because the indices are repeated. So this becomes a bar alpha prime beta prime. If we replace the dummy indices in the final expression, so we write it as a bar alpha prime beta prime is equal to del x bar alpha prime del xi del x bar beta prime del xj a of ij. Now the dummy indices, or we can change this point. So the inverse relation to this is a bar alpha beta is equal to del x bar alpha del xi del x bar beta del xj a of ij. For this, the transformation relation is a bar alpha beta is equal to del xi del x bar alpha, this is alpha, del xj del x bar beta a of ij. And for mixed tensor, the inverse relation is this is x bar alpha del xi, this is the contravariant component del xj del x bar beta a of ij. So these are the transformation relation and these are the inverse transformation relation. I have obtained this relation from this. You can find out this relation starting from this and this from starting from this. So these are the three types of tensor of rank 2. Note that a tensor of rank 2 has exactly n square component. In three-dimensional space there are 9 components for a tensor of rank 2. You have already encountered such quantities, that is the susceptibility tensor, conductivity tensor, and the tensor in the connection with the elasticity. These are all tensor of rank 2. Another thing I want to tell you that the Kronecker delta that we generally used here, we have written in vector notation the Kronecker delta one suffix, one superscript, another subscript. That means it is a mixed tensor of rank 2. Let me show that the Kronecker delta is indeed a mixed tensor of rank 2. So Kronecker delta delta is a mixed tensor of rank 2. Let us start with the definition. This is Ij is equal to del xi del xj. We now use the figure of coordinate transformation. So we write del xi del x bar alpha del x bar alpha del xj. Here the sum over alpha is implied. We further rewrite it as del xi del x bar alpha del x bar beta del xj, and there is a delta notation beta alpha, and it is in barred system. So if we consider these two relations, it is indeed that the conical delta do transform like a mixed tensor of rank 2. So this is the I, this is the contravariant component, and this is the covariant index. So this is a I have made a mistake there. So, now we shall discuss few symmetry properties of a rank 2 tensor. We consider a rank 2 tensor which is symmetric. If we symmetry aspect, we shall first consider a contravariant tensor, symmetric tensor. A contravariant symmetric tensor is contravariant symmetric tensor of rank 2 is defined as Aij is equal to Aj. Now, our aim is to see whether this symmetry property is being carried out into other coordinate system or not. In order to study this, we write A bar alpha beta is equal to del x bar alpha del xi del x bar beta del xj Aij. This is the transformation relation of a contravariant tensor of rank 2. Now we perform this on interchanging between alpha beta and Ij. That means I and j are interchanged together with alpha and beta. This left hand side becomes beta alpha. This is del x bar beta because alpha is beta. This is del xj. This is del x bar alpha del xi a of ji. Since a of ji is equal to a of ij, we can write it as, we are writing this term first, del x bar alpha del xi del x bar beta del xj a of ij. This is nothing but the expression for a bar alpha beta. So a bar alpha beta is equal to a bar beta alpha if the symmetry between if a contravariant tensor of rank 2 is symmetric in one coordinate system, it should be symmetric in other coordinate system. For covariant tensor, symmetric covariant tensor, symmetric covariant tensor of rank 2. This is Aij is equal to Aji. Let me first write the transformation relation A bar alpha beta is equal to del xi del x bar alpha del xj del x bar beta is equal to A of ij. On interchanging between alpha beta and I and j, what do we get? We get A bar beta alpha is equal to del xj del x bar beta del xi, this term, del x bar alpha A of ji. Since A of ji is equal to A of ij, we derive it as del xi del x bar alpha del xj del x bar beta A of ij. This is nothing but A of alpha beta. So the symmetry is retained. If we have a covariant vector symmetric tensor which is symmetric in one coordinate system S prime, then the symmetry is carried over to S prime frame. But there is a difference. Now, so far as mixed tensor is concerned, so we have a mixed tensor, symmetric mixed tensor of rank 2. It is symmetric, so it is Aij is equal to Aji in S frame. So what happens to other frame? So we write the transformation relation A bar alpha beta is equal to del x bar alpha del xi del x bar beta, sorry, del xj del x bar beta A bar alpha beta A of ij. Now we interchanging between alpha beta together with I and j. What do we get? We get A bar beta alpha is equal to del x bar beta del xj del xi del x bar alpha A of ji. Now we know that A of ji is equal to A of ij, so we rewrite it del xi del x bar alpha, the second term, del x bar beta del xj A of ij. But note that this is not Aij. Sorry, this is not A bar alpha beta. So what we see that if we have a rank 2 tensor, covariant or contravariant, if it is be symmetric in one coordinate system, it will be symmetric in all other coordinates and the tensor transformation. But a symmetric tensor of rank 2, if it is be symmetric in one coordinate system, the symmetry is not carried over to the other coordinate system. For higher order tensor of still higher order, we can conclude that if the tensor is symmetric in one coordinate system with respect to the interchange of either two covariant indices or two contravariant indices, then this symmetry is carried over to other coordinate system. But if the tensor is symmetric with respect to interchange of one covariant one covariant index with another contravariant index. So this symmetry is a special symmetry which is observed only in one coordinate system. That symmetry may not be carried over to other coordinate systems. So that's all about our introduction to rank 2 tensor. In the next class, we shall introduce ourselves with tensor of higher rank, and then we shall pass over to what exactly tensor algebra. That is the equality between two tensors, the product of two tensors, etc.